Hi everyone. Today I want to do a short video about something called the handshaking lemma and how we can use it to find the bounds of the number of edges in a simple connected graph. So I'll define what connected graph means later, but the general idea of the handshaking lemma is based on a little puzzle. Suppose there's a party and people are meeting each other and shaking each other's hand. And then at the end of the party, let's say you ask everyone how many hands they shook. If you tally up all those numbers, the answer they give you, and add them up, prove that the answer will be even. So it's a bit abstract, but if you think about it correctly, the answer should be kind of obvious. Another variation of a more modern approach is to prove that the number of match notifications on Tinder, for example, since its inception, must be even. So if you think about that a little, what happens when you have a match on Tinder? So who gets notified on Tinder? Two people get notified, right? Right, the people who get matched. So despite not knowing how many matches there are in general, suppose there are n matches. How many people get notified? But for each match, 2 people get notified. So that's 2 times n notifications. But 2n is even. So regardless of not knowing how many matches there are on Tinder, could be millions, we know that how many notifications get sent out, regardless of how many matches there are, it must be even. So this is the same answer to the handshaking lemma. How many hands were shook at the party? Well, for each pair of people shaking hands, 1 handshake is equal to 2 hands that get shook. So let's explain that in a graph theory perspective. So this is the handshaking lemma. And we already proved it. That the sum of the degrees of the vertices, and we'll explain why this makes sense, is equal to twice the edges in the graph. So why? For each edge, so think about this as for each match, for each handshake. So for each edge, Vi, Vj, so Vi is you and Vj is the person you match with. You have 1 to the degree of Vi, and you add 1 to the degree of Vj. So net total is plus 2 to the sum of the degrees. So for how many, for n number of edges, there will be 2n degrees total. And we can even do this for multigraphs. So for each loop, Vi, Vi. So remember a loop, there's 2 degrees that get added, right? It's plus 2 degrees of Vi. So for each edge, there's net total of you're adding 2 to the degree sum. So we can write this in math notation that for any graph, the sum of the degrees of Vi, so for I equals 1 to n, is equal to twice the number of edges for any graph. This is for simple graph, for multi-connected graph, multi-graphs. This is always true. It's a very powerful lemma, and even though it's almost very obvious, for every edge there's always going to be there's always two vertices that are acting in every edge. And for a loop, of course, it counts twice because it's looping on itself. So what we'll be able to do is say we're going to find upper and lower bounds for the edge set for any simple connected graph. So we talked about simple last time, but just to reiterate, a simple graph, oops, sorry. So a simple graph is a graph with no multiple edges or loops. And let's talk about what a connected graph is. You can kind of guess what the definition is based on the name. So connected graph is, we can formalize the definition as for any two vertices, for any vi, vj, in the vertex set, there exists a path vi dot 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 vj. So a path from vi ending at vj. So, for example, of a disconnected graph, this is disconnected because there is no path connecting connecting this vertex here to this vertex there. So that's what a connected graph is. So a graph that you can always find a path between any two vertices. So, so a simple connected graph is a connected graph that has no loops or multiple edges. So let's think about the upper bound for the number of edges. Oops. So just think about what that means, right? What is a graph that is has the maximal amount of edges? Max edges in a graph. Let's call the number of vertices equal to n. So for this graph to be maximally connected, every vertex is connected to every other vertex. But not connected to itself. Right? Because this is simple graphs, we can't have loops. So what does that mean? That for every vertex in the vertex set, the degree of that vertex should be n minus 1. Right? Each vertex is connected to every other vertex. So, and then by the handshaking lemma, we know that the sum of the degrees should equal twice the edge set. So if every vertex has degree n minus 1, and you're adding that n times, how many edges are there? Well, twice the edges is n times n minus 1. So that means that the edges is n times n minus 1 over 2. So this is just by using the handshaking lemma. You don't need the handshaking lemma to prove this, so I'll let you try to think about that. How could you prove this out the handshake lemma? You might have to use some induction or understanding how to sum up integers. So, but we don't need that. If we just know about the handshaking lemma, we can we can just utilize this formula immediately. So this is the upper bound for the edges in a graph. So while we're here, we have a name for such a graph that is maximally connected like this. This is called a complete graph. So Kn would be our symbol for a complete graph, is called the complete graph on n vertices. And I'll let you think about why the complete graph is unique, right? That they're all complete graphs of the same number of vertices are isomorphic to each other. We can't find a non-isomorphic graph that is also complete. So I'll let you think about that, but it's not too hard to see. So for example, K5, so every graph, every edge, so every vertex gets connected to every other vertex. So you get something that looks like this. This is K5, K4, so this is maximally connected. So the number of edges here is 5 times 5 minus 1 over 2, which is 20 over 2 is 10. And then number of edges here is 4 times 4 minus 1 over 2, which is 12 over 2, which is 6. This is a great upper bound, and but we'll find out actually the lower bound is a bit harder to see. Well, let's talk about it. So here's a claim. Not V, but a minimally connected graph must not have any loops, or cycles rather. Let's see why this is true. Suppose we have some graph. We don't know what it looks like, but at some point there's a cycle. And let's explain why this cannot be minimal. Well, it's not minimal because let's say if we remove an edge here, we can still traverse a path from this point to this point by going around the other way. So this is not minimally connected. Right, if something is minimally connected, you would imagine if a graph is minimally connected, removing an edge should disconnect it. Oops, excuse me. Not so removing any edge. So, right, that makes sense. If you claim that you have a minimally connected graph, that means that if you remove an edge and have it still be connected, well, then that graph is minimal, right? So you just contradicted yourself. So the smallest the graph with the least amount of edges should be so that if you remove an edge, it suddenly disconnects the graph. So let's prove or explain about what that graph is called. So a graph that's connected with no cycles is called a tree. So the name is, the definition of a tree is in its name, right? Think of a tree, right? There's no loops in a tree. The branches of a tree don't loop back on in itself. Right? The trunks of a tree don't, loop back and grow back into the trunk. So trees have no loops or cycles. So another way you can say this is it's a consequence of this statement. Any path vi to vj is unique. And why not? Suppose there are two paths. Right? If you have two paths from vi to vj that are different, right? That means at some point it's going to branch off. They could have common paths, but at some point it'll branch off and come back to vj. But you can create a cycle by concatenation, right? Take this path and concatenate it with the reverse path, and at some point you'll make a loop or a cycle. So then when you hit the common point, that makes a cycle. So this is an equivalent definition of a tree. Not only does a tree has no cycles, but also a tree is a graph where all paths are unique. In general, if you don't want to think about connected graphs, any graph with no cycles is called a forest. Right? Every like mini graph, if it's disconnected, right, that there should be within your graph there are smaller graphs that are themselves trees. So if you have a bunch of trees, that makes a forest. It's kind of a clever name. All right, but one thing we don't know, and really see how it's not true, but while we had complete graphs are isomorphic to each other, it is not true that trees are isomorphic to each other if they have the same number of edges or vertices. Here's a very simple example. Here's a tree with 4 vertices. And here's another tree with 4 vertices. But these are not isomorphic. Why not? It's because the degree sequence is different. The degree sequence here is 1, 1, 1, 3. The degree sequence here is 1, 1, 2, 2. So these are non-isomorphic trees of 4 vertices. So that leads itself into a question: can you have two non-isomorphic trees with the same number of vertices but different number of edges? Right? We claim that the number of edges in a minimally connected graph, kind of intuited that really should be a tree. But can we make trees with a smaller edge set? And the answer is going to be no, but we're going to prove why. So first of all, we need to have a little baseline for how many edges are in a tree that at least we know how to construct. And here are two examples of a very simply constructed tree on a general n vertices. Let's say our vertex set has n elements. And I'm going to construct a tree very simply by just a line. So this is obviously a tree, right? I'm not ever looping back on itself. And I have n vertices here. And the degree sequence is 1, 1. Right? The vertices at the end have degree 1. And every vertex in the middle has degree 2. And how many degree 2 vertices are there? Well, if there are n vertices and 2 of them are 1, the rest are 2. That means there are n minus 2 degree 2 vertices. So we can use the nice handshaking lemma. By the handshaking lemma, that means that 1 plus 1 plus n minus 2 times 2, right, there are n minus 2 of them, is going to equal twice the number of edges. So that's 2 plus 2n minus 4 is equal twice the edge set. So this is 2n minus 2 is equal twice the edge set. And n minus 1 is equal to the edge set. All right, so we know what a tree looks like on n vertices, and we have found one that has n minus 1 edges. So that's going to be our assumption. Okay, well, I want to show, or at least it would be very nice, if all trees with n vertices had n minus 1 edges. And that's the easiest one to see, but here's another pretty easy one to see, called a star graph. So let there be one vertex, and let it connect to every vertex, every other vertex. But none of the other vertexes are connected. So there are n vertices, and you have one vertex with degree n minus 1. And then you have n minus 1 vertices of degree 1. So you have one vertex that's degree n minus 1. And you have n minus 1 vertices of degree 1. And by the handshaking lemma, the sum of this should equal twice the edge set. So what is this? It's 2n minus 2 is equal to twice the edge set. And n minus 1 is equal to the edge set. All right, so here's another example. It's a pretty easy example of a tree that has its edge set as n minus 1. Okay, so what we want to prove is that this will be our goal to prove. A connected graph G is a tree if and only if the edge set is n minus 1. So we're going to say that only trees have edge set as n minus 1. So all trees will have n minus 1, and no other type of graph has a edge set of n minus 1. Okay, so let's prove a quick little lemma to help us prove this theorem. If a graph G has its edge set equal to n minus 1, and it's connected, we want to show that there must exist a vertex of degree 1. So how could we prove this? So we'll prove this by contradiction. Suppose not. Suppose all the degrees are 2 or more. So by our handshaking lemma, for the sum of the degrees equal to twice the edge set, which we say is n minus 1, if I replace all the degrees with 2, then this becomes smaller, right? Because the smallest, we're saying the degree is 2, so nothing else is smaller than 2. So they're all bigger. So how many 2 are there? There's 2n, then 2 times n minus 1, but here we get a contradiction. When we divide by 2, we get n is less than or equal to n minus 1, which is a contradiction. This is false. So that means our claim was false. So that means there must exist a vertex of degree 1. All right, so let's take that fact, and what we're going to do is we're going to make a statement about graphs with their edge set of n minus 1. So we have our edge set is equal to n minus 1, and there is at least one of degree 1. All right, so imagine this. We have this graph, and we have out here some vertex of degree 1. So there's this whole graph going on, and here we have a vertex of degree 1. What happens if we remove that vertex and the edge connecting it? So remove the degree 1 vertex. So what happens is that the graph, its new vertex set, well, you're subtracting one of the vertices, so it's n minus 1, and the new edge set, it was n minus 1 and then became n minus 2. So now also think about what are the consequences of removing a vertex 1 degree, or a degree 1 vertex? Well, if there was a cycle in this graph, then removing a degree 1 vertex wouldn't do anything, right? If you had a cycle with no repeating edges in the path, well, there can't be any degree 1 vertex there, right? So removing a degree 1 vertex does not affect how many cycles there are. That's very important, because what we're gonna show is we're gonna do this a bunch of times, and we'll find out that we'll get a tree in the end. And if at every point we're doing this, we're deleting a vertex, it will not affect the number of cycles, we'll find that our original graph with n minus 1 vertices, or edges rather, had no cycles to begin with. So the point is, look at this new graph that you get when deleting that vertex and edge associated with it. Well, you have a case that satisfies the lemma. You have, so now our new n is n minus 1. So you have, in this case, now there is a vertex of degree 1. Right? This satisfies the lemma. You have n minus 1 vertices and n minus 2 edges. So to make it a little bit clearer, if k is equal to n minus 1, the edge set is equal to k minus 1. So it satisfies it for k. So now just keep on doing this. Do this. How many times we want to do it? Let's do this n minus 2 times. What do we get in the end? We have a vertex set equal to 2 and an edge set equal to 1. And what is that? It's a tree. Here's 2 vertices, and here's an edge between it. By the way, you could do this one more and just get a very boring tree. Vertex set equals 1 and the edge set is 0. This is called a null graph, or a graph with no edges, or empty graph sometimes you might call it. So So now we use this kind of fact that removing a degree 1 vertex does not affect the number of cycles in a graph. So at every point in our iteration, we have removed degree 1 vertices. So since we've landed on a tree, after doing this so many times, that means our original graph here, this must have been a tree, because it has no cycles. So that proves it. So if a graph has n-1 vertices, it is a tree. So now you prove the, that was just one direction, right? All n-1 vertice graphs are trees. So now let's do the reverse. If you have a tree, then it must be n-1 edges. So now the other direction. All trees have n-1 edges. And this one is actually a lot easier to construct. So let's just take the almost simplest tree, and add an edge to it. Add a vertex and edge to it. Particularly, let's add a degree 1 edge. Oh, sorry, degree 1 vertex. Very similarly, just as removing a degree 1 vertex does not add does not affect the number of cycles, adding a degree 1 vertex would not add a cycle. It would not affect the number of cycles. So at every point, if I add a degree 1 vertex to a tree, it will never create a cycle. And in our base case, we know what the vertex and edge set is. Where we know this is the vertex set is 2 and the edge set is 1. So when I add a degree 1 vertex, I'm adding 1 to the vertex set, and I'm adding 1 to the edge set. I know in my base case, for v equals 2 and e equals 1, it satisfies e is equal to n-1. So you can do this inductively. I won't do the precise proof, but it's not too hard to do the induction here. That means that all trees have n-1 vertices. So we have proved it. We have proved our upper and lower bounds. So conclusion. So we're going to use this theorem that for a simple connected graph, G is a tree if and only if the edge set is n-1. And we can, using all these theorems together, we can say that for G, a simple connected graph, the bounds on the edge set is n times n-1 over 2. Remember, this was our complete graph. Is its upper bound, and its lower bound is n-1, which is our tree. So, so we see kind of two extremes of connectivity. The complete graph is the most highly connected graph, while the tree is the least connected graph. So here we have nice bounds on our edge set. n-1 is the lowest as a tree, and n times n-1 over 2 is the number of edges in the complete graph. Now notice if you just multiply by 2 everywhere, you can get a similar definition for the sum of the degrees. 2n minus 2, we know that twice the edge set is the sum of the degrees. and this makes n squared minus n. This is still for a simple graph, simple connected. So hopefully this was a nice little lesson on the handshaking lemma and finding bounds on the edge set for any simple connected graph. Thank you for listening, and see you again. Thanks.